So, hi everyone. Well, let me remind you that the main purpose of your studies is what? Is to learn how to solve problems or how to apply laws of physics in solving problems. That is the main purpose, to obtain this ability to solve various problems in physics. And so we will solve as many problems here as possible. Last lecture, when I was solving a problem on static equilibrium of a ball hanging on two threads, I made a mistake. I wrote cosine over sine equals something like, tangent. This is not true. Surely this should be cotangent. Please make correction in your notebooks if you have not done so. Please correct this mistake. By the way, thinking about mistakes, when a student makes a mistake, it's mostly due to poor knowledge. When a professor makes a mistake, you know why? Because he has 2 or 3 thoughts at the same time. He's thinking about 2 or 3 different things. That's the problem. That's not, for me, in order not to make a mistake, I have to concentrate on one single thought. If I distract on several thoughts, different thoughts at the same time, then the mistake is absolutely inevitable. Okay. We will consider some more problems today. Problem number 76. So a hunter discharges his gun from a light inflated boat. So we have the surface of the lake, a boat, and the hunter firing at some direction. What velocity will be imparted to the boat when the gun is fired if the mass of the hunter and the boat is m? So we know the total mass of the hunter and the boat, that is 70 kilograms. The mass of the shot is 35 grams. So the bullet here flying is 35 grams. And the mean initial velocity of the shot is also given. It's 320 meters per second. So that's the initial velocity of the shot. The barrel of the gun is directed at an angle alpha. And alpha is also given at 60 degrees. So we have to find what? The velocity that will be imparted to the boat. So after the shot is fired, the boat will go this way with some velocity u, which we don't know. We have to calculate it. Very simple problem on the law of conservation of momentum. If we consider the process of firing a shot at some angle to the horizon, we understand that we can consider the momentum of the bullet in vertical direction and in horizontal direction. The vertical component of the momentum and the corresponding force will be balanced by the reaction of water. The vertical component cannot result in any motion of the boat in horizontal direction. The vertical component of the momentum may result only in some oscillation of the boat, which will be immersed deeper into the water and then go up and then down again. There will be some oscillations because of the vertical component of the force acting on the bullet and the corresponding force of reaction, which is directed downward on the hunter and the boat. I'm not drawing and showing these forces here. It's enough just to discuss them. So we can neglect the vertical component because it results in no shifting of the boat in horizontal direction. In order to find the horizontal velocity of the boat, we have to take into account only the horizontal component of the momentum. The momentum of the bullet is m v0. The horizontal component, that is the x component of momentum, will be m v0 cosine alpha, the adjacent leg in triangle. That is the horizontal component of the bullet momentum. And now we can write down the law of conservation of momentum in horizontal direction. So initial momentum, total momentum, initial was 0. And it will remain 0 because no external forces are acting on the system in horizontal direction. No external forces. No wind, no water flow, nothing. Nothing is given in this problem. In horizontal direction, no external forces. Therefore, the initial momentum will be preserved and it will remain 0. So the final momentum will be what? In positive direction, we have the momentum of the bullet. And in negative direction, the momentum in negative direction, the vector is directed oppositely the positive direction of x-axis. So this will be the negative sign, and this term will come into this equation, will enter this equation with negative sign. That will be the mass of the hunter and the boat and their final velocity after the shot. That will be the final momentum of the system. And what is it? It must be 0 because of the law of conservation of momentum. It was 0 before the shot, total momentum of the system, and will remain 0 after the shot because no horizontal forces are acting on the system. Well, from this equation, we can find the velocity of the boat after the shot, which is m v0 cosine alpha divided by m. In this problem, all the physical quantities are given. So we have to use these numbers in order to calculate the final velocity. The final answer will be some number because the problem gives you all numbers. So we have to calculate it and obtain the number. Okay, let's do it. M, 35 grams. 35 grams in kilograms is this quantity. V0, 320 meters per second. Then cosine alpha, if alpha is 60 degrees, then cosine will be 1/2. And in denominator, the mass of the boat and the hunter, 70 kilograms. 70. Everywhere I omit the units of measurement because all the units are taken in international system. Kilograms, meters, seconds, everywhere. International system. So the final answer will also be obtained in the international system. The velocity in the international system is meters per second, surely. So we have to calculate. You don't use calculator for such simple formulas. Note that we can divide by 10 and cancel 0. Then 32 divided by 2 will give you 16, right? And 35 divided by 7 is 5. So I divide by 7. What remains here is 1, and what will become of this number? 0.005. 7 times 5 is 35. So 5 times 32, just digits, 3, 6, 0. And then where to put the decimal comma or decimal point? Sorry? Five times 32. 10, yes, sure. Sure. That's it. 5 times. What's wrong? Yes, 16, certainly. Not 32. I have already divided. Yes, certainly. That's just 2 times less. Right? And 3 digits after the decimal point. So 1, 2, 3. That's in international system. 0.08 meters per second. That will be 8 centimeters per second. Yes, exactly. Yeah. Eight centimeters per second. That will be the velocity of the boat in horizontal direction after the shot was fired. Because of the recoil of the gun, the hunter and the boat will experience some push from the gun after the shot at the moment of the shot. So the boat will move at this velocity. Okay, that's it. So what's important in such problems? First, we have to make sure that no external forces act on the system during the process which we consider. And if there are no external forces, then the momentum is conserved. That is, the final momentum equals the initial momentum, if no external forces. If only internal forces are present in this process, then the momentum remains the same. The final momentum equals the initial momentum of the whole system. Next problem, number 85. a hoop is placed on an absolutely smooth level surface. So we will look from above on the surface of the table where there is a hoop. A hoop is placed on an absolutely smooth surface, so there is no friction. A beetle alights on the hoop. Here, a bug. What trajectory will be described by the beetle and the center of the hoop if the beetle begins to move along the hoop? So the beetle begins to crawl in this direction along the hoop. And we need to show the trajectory of the beetle and the center of the hoop. The radius of the hoop is given.
No, it's stuck.
The mass is given of the hoop, and the mass of the beetle also is known. We must find the trajectory. The question to this problem looks different from the question to the previous problem. Here we had to find the velocity, and here we have to find the trajectory. That is the curve described by the beetle against the table. The question is different, but the physics laws are the same. If there are no forces of friction and no external forces, then the momentum is conserved in this system of two bodies, the hoop and the beetle. The momentum is conserved. It means that the final momentum is the same as the initial momentum. The initial momentum is zero, so it will remain zero during all the process of motion. As the bug crawls along the circle, the total momentum is conserved. What does it mean? It means that the center of mass of the system remains at the same point. The center of mass is at rest. How to calculate the center of mass? For example, how to find this distance, or how to find this distance, which is r minus x. The center of mass of the hoop lies in the center O. So according to the general formula, mx should equal to small m times r minus x. I remind you the general formula for the center of mass coordinate. That is m1 r1 plus m2 r2 divided by total mass. If you have more than two bodies, then you have more than two terms in this formula. In our problem, we have only two bodies, and r is the radius vector of the center of mass. If we put the reference frame in this point, in point C, then r will be equal to 0. If the reference point is here, then the distance from this point to the same point is 0. And so from this formula we will have m1 r1 plus m2 r2 equals 0. What is r1? This vector. The vector showing to the first mass, the center of mass of the hoop, from the origin of coordinates. And R2 is the vector beginning at the origin and ending at the middle. That is R2. So if we introduce horizontal axis and find the projection of these vectors on horizontal axis, then we will find what? That vector R2 should be positive, it looks in positive direction, and vector R1 is negative, it looks in negative direction. So we can find that M times positive quantity R minus X, and this is negative, minus M X equals 0. So that's that expression, that equation we obtain from the definition of the center of mass. We may start from the definition and we arrive at this equation, which is certainly the same as what we have written from the very beginning. So if you are not sure how to solve the problem, please start from the very beginning, from definition of physical quantities, and then derive the equations step by step. But if you are experienced in this process, you can immediately write down the final expression, which is obvious. It's obvious for people who are experienced in this, in solution of such problems. But if you are not experienced, you may not be able to immediately write such an equation. In this case, you should start from the definition of physical quantities involved in this problem. And if you start from the definition, you will make no mistake. If you start from the definition of the physical quantities known to you, the definition of velocity, the definition of acceleration, the definition of momentum, the definition of the center of mass. If you start from the definition, you will make no mistake, unless algebraically everything is done correctly. Okay, here from this equation we must find unknown quantity x, this distance. How can we do it? Oh, sorry, there are two different masses here, certainly. The radius vector R minus X looks at the beetle, but the radius vector X looks at the center of mass of the hoop, and the mass of the hoop is capital M. So this should be capital M. M2 equals to capital M in our particular problem, in our notations. So what we will have here, MR equal to M plus mx. And so the unknown quantity x equals mr over capital M plus small m. That is the distance x from the center of the hoop to the center of the mass, to the center of mass of the system of two bodies. We have two bodies, the hoop and a small beetle crawling along the hoop. And we know that as there are no external forces acting on the system, the center of mass will remain at rest. The point C will remain at the same place. It will not move. Everything other may move here because there is no friction. But the point C will remain here. Distance x will remain constant. It does not depend on time. It's expressed only through such quantities which remain constant. The radius of the hoop does not change. The mass of the beetle, the mass of the hoop do not change. So this is constant in time. The distance from the center of mass to the center of the hoop remains constant. And also the distance from the center of the hoop to the beetle remains constant. What does it mean? The beetle moves and its distance from the point C remains constant. It means that the beetle moves along the circle which has the center at point C. The beetle moves along this circle. And the hoop will move also in its own circle, which will have radius x. The circle about point C. The center of the hoop will go along this trajectory with radius x. And the point C, the center of mass, will remain at rest. It will not shift in no direction. So when the beetle crawls here, the center of the hoop will be shifted here, always on the same line which goes through the center of mass. And so they will move. The beetle moves here, the hoop moves here, but both the beetle and the hoop describe circles and move along the circles with the center in point C. And the radii of these circles we know. We know the radius x, and we know certainly the radius r minus x. The radius remains constant in time. As the beetle crawls, the radius remains constant. Why the hoop moves? Why does it move? Because the beetle pushes the hoop. While it crawls, it pushes the hoop, and the hoop should move because there are no friction forces here. The only force is the force between the beetle and the hoop. So as the beetle moves, the hoop should also move. The beetle moves here, and the position of the and this point of the hoop will move in different direction. So we have found the trajectory. The question to this problem was to find the trajectory of the beetle with respect to the surface of the table. Yes, we have found this trajectory. It's a circle with a given radius. So the question, so we have found the answer to the question of this problem. Before we proceed with the solution of the next problem, we have to consider some interesting theorem. Very useful theorem. A theorem on the motion of the center of mass of the system of bodies. Let's consider a system of material particles, particle M1, particle M2, etc. Maybe particle M3, etc. Maybe many particles. Each particle may have its own velocity and its own acceleration. And the particles may somehow interact with each other. So there may be forces of interaction which are directed along the same line and opposite in direction. And also these particles may interact, not necessarily attracting each other, this may be a repulsion. And these particles may interact and may not interact. It doesn't matter. So we consider a general case. Any number of material particles interacting between each other. And also, apart from these internal interactions, we consider some external forces. So all these forces here are internal. Internal force 1 and internal force 2, internal force, well, anything, 3, internal force 4. It doesn't matter how you count these forces. But also there are external forces acting on the particles. Some external forces. Let me denote external forces by this symbol. And on each particle there may be an external force, maybe on one particle, maybe on two, or on every particle. It doesn't matter. So we consider the general situation. What will be the acceleration of the first mass? The acceleration will be defined of the first material particle. Its acceleration, due to Newton's second law, will be defined by the net force acting on this particle. Net force is the vector sum of all forces acting on it. Vector sum of all forces. And this vector sum of all forces will be the vector sum of all internal forces plus the vector sum of all external forces. The same is true for the second particle. Its acceleration, according to the second Newton's law, is defined by the net force acting on it. And in order to somehow distinguish between these two forces, we have to put different indices here. So these forces, net force acting on the first particle, and this is the net force acting on the second particle, net force acting on the first particle from external bodies, and net force acting on the second particle from external bodies. These are different forces because they act on different particles. They should not be the same. They may be different. And so we have to use different notation. We should not use the same notation, the same letter for different quantities. And so on for the third particle, for the fourth particle. We may have 100 particles. I don't need to write down 100 similar equations. All of them will look like this. But there may be 100 equations or 1,000 equations. It doesn't matter. All the equations will be the same. Now I will add all these equations together. I will add all of them, no matter how many. I will add them. What will be the result? The result will be the sum of all internal forces. I will indicate it using this. The sum of all internal forces, the sum by index k, plus the sum of all external forces, and all this will be equal to what? m1 a1 m2 a2 plus etc. so on and so on, depending on the number of particles. Each particle will give its own term in this equation. When we find the sum of all internal forces, we must take into account the Newton's third law. The Newton's third law says that if you have a force of interaction between two particles, then one force acting on the first particle equals the second force acting on the second particle, and these two forces are equal in magnitude and oppositely directed. It means that when we add the two vectors, we obtain zero. They will cancel. All the internal forces will cancel due to Newton's third law. This is a subtle moment. Actually, these two forces are applied to different particles. And therefore, when we consider the system of two particles, we never cancel the internal forces. They are applied not to the same particle, but to two different particles. So they don't cancel. But here, mathematically, we just add the vectors. Here we have no information to which particle the internal forces are applied. Here we have just a mathematical summation of vectors. And therefore, we somehow forget, we don't have information to which particles these forces are applied. And so we know that if there is such vector, then necessarily there is another vector. And when we add two vectors oppositely directed and equal in magnitude, we obtain zero. Inevitably, all the internal forces, when summed up, will yield zero. So only external forces should be added here. And this sum of all external forces is just the net external force acting on the system of particles. The net external force. The vector sum of all the external forces acting on different particles. So what we obtained, the net external force acting on the system of particles is the sum of mass times acceleration of each particle. Let's multiply this expression by the total mass of all the particles and divide at the same time by the total mass. Nothing changes. These two quantities will cancel each other. But m is the total mass of all particles. I just introduce this quantity, and I have the right to multiply our expression by this quantity and divide at the same time so that nothing changes. Nothing changes here. So this quantity remains on its place, and what is given by the remaining expression is m1a1 plus m2a2 plus etc. divided by total mass. And this is, if you look at the definition of the center of mass, then you will easily understand that this expression is equal to acceleration of the center of mass. Total acceleration of the center of mass. So what we obtain here is the total mass of the system times acceleration of the center of mass of the system. So we have proven very important theorem, which can be written as follows. The net external force acting on the system of particles equals its total mass of the system times acceleration of the center of mass. Center of mass acceleration. It's not centimeters, it's the center of mass. This is a very important theorem which plays a great role in many physical processes. So if we have an arbitrary system of particles, what does it mean, arbitrary system? It means any rigid body. For example, this piece of chalk, because it consists of many atoms or molecules, each atom is a particle. So it's also a system of particles. Billions and billions of particles, but anyway, arbitrary system of particles is an arbitrary rigid body. Or it may be a liquid in a glass, or it may be a gas in a vessel. So it may be anything. What is an arbitrary system of particles? It's anything, absolutely any object. It may be a galaxy, or it may be a solar system with its planets and sun. Anything. And we have found that the center of mass of this system of particles moves with acceleration if some external forces act on this system of particles. And we have to find the net external force, that is, we have to find the vector sum of all external forces acting on this system. That is the vector sum of all internal forces. Internal forces cancel each other. We have to take into account only external forces acting from outside objects. And the mass, total mass of the system of particles. That's a theorem looks like second Newton's law, but what is the acceleration of the center of mass? The center of mass is some point in vacuum. Nothing is here. All the particles are somewhere in other places. Here is nothing. And we consider the acceleration of this imaginary point. It's not always inside the rigid body. Sometimes it's somewhere far away from other points. So we consider the acceleration of this imaginary point, and the acceleration of this point obeys the formula looking like the second Newton's law, where m is the total mass of the system of particles and F is the net external force acting on this system of particles. Very important theorem, which plays a great role in many physical processes. Now we will consider a problem that can be solved with the help of this theorem. We have to take into account this theorem when solving many problems. Problem number 86, or problem number 86. A wedge with an angle alpha at the base can move without friction on the surface, on the smooth surface of the table. So we have a wedge or inclined surface with angle alpha, and it can move without friction on the surface of the table. And here is the mass and the string goes over the pulley, and another mass is here, and it can move either without friction or with some coefficient of friction. So these masses are given m1 and m2. two masses are connected by a string which passes over a pulley. And the question is, at what ratio between masses m1 and m2, what should be the ratio m1 over m2 such that the wedge remains at rest? If these masses move or if they don't move, if the coefficient of friction here is given, the coefficient of friction is given at this surface. So it's clear that if there is no friction, then either the two masses will go to the right, mass m1 will go down and will pull mass m2 upward, or probably mass m2 will go down if the mass m1 is much smaller. Then m2 will go down and will pull the mass m1 up. Something like that. So the two masses will move either to the right or to the left if there is no friction. And we have to find the ratio of masses which ensures for the wedge to move to the right, to the left, and or to the right. So the wedge can also move. Sometimes it will not move. And we have to find at what values of this ratio the wedge will go to the right, and at what values of this number of this ratio the wedge will go to the right, to the left or to the right. That's it. That's the question to this problem. Well, this problem includes everything you know. Newton's laws, laws of classical mechanics, and the law of conservation of momentum, and the theorem which we have just proven, the theorem on the motion of the center of mass of the system of bodies. Here we have a complicated system of bodies, a wedge and two blocks. And no external forces are acting on this system, nothing from outside. Only the gravity pull and the reaction of the table. But these two forces will cancel each other. The gravity pull directed downward and the reaction of the table surface directed upward. As the wedge is unable to jump up and will surely not go down through the surface of the table, then these two forces cancel each other, and we may forget about them. We don't take them into account. So what we take into account, anything happening here except the forces, except the gravity forces and the reaction of the table surface. And according to this theorem, we know that if no external forces act on this system in horizontal direction, then the center of mass motion will obey this equation. And if no external force acting, it means that external F external is 0. And if it's 0, then the acceleration of the center of mass is 0. So acceleration is 0, it means that the velocity is constant. And it means that there is certainly such an inertial reference frame where the velocity of the center of mass will be 0. In some other reference frames, the velocity will be constant. But there is one reference frame, well, probably related to this classroom, and you are in this reference frame, in which the velocity of the center of mass is 0. So if the center of mass is at rest, we don't know where the center of mass is, but somewhere the horizontal coordinate of the center of mass may be somewhere, for example, here. We know that the center of mass is at rest, whatever happens, no matter how these loads move. The center of mass of the system remains at the same point. Why? Because no forces in horizontal direction act on this system. And if no forces, if the forces, external forces, are zero, then according to this theorem, acceleration is zero. And therefore, in our reference frame, the center of mass will remain at rest. So, starting from this point, we understand that if this block goes downward, then it will shift right to the right, and this block will go up. And so the center of mass of these two blocks will shift to the right, and therefore the wedge will go to the left, so that the center of mass of the system remains at the same time, at the same point. That's proven. If this block goes to the right, then the wedge will go to the left. And vice versa. If it goes to the left, then the wedge will go to the right. So that the center of mass of the whole system remains at the same place. So, suppose this block moves at some given point in time, at some given moment in time. Suppose this block moves with velocity v, moves at velocity v with respect to the surface of the wedge. Then the wedge will move in opposite direction with some velocity u. So the momentum of this body in horizontal direction will be m2 v cosine alpha. The momentum of this body in horizontal direction with respect to the surface of the wedge. But the wedge moves in opposite direction. And so this body shifts in a unit of time, shifts at this distance, and the wedge goes in opposite direction. So the resulting shift of this body will be horizontal shift with velocity v cosine alpha minus u. That will be the resulting displacement of this body. Velocity is the displacement per unit time, so we choose a small unit time, and we see that this displacement directed here, and the surface goes in opposite direction here. So the actual displacement will be this one, with respect to the table. And this is with displacement with respect to the surface of the wedge. So such will be the horizontal momentum of the body m2 if it starts moving in this direction. And the block of mass, of a larger mass, let's denote this mass by capital M, the mass of the wedge, will go in opposite direction with velocity u, so it will have momentum m times u in opposite direction. so that the total momentum in horizontal direction will be the momentum of the m2 minus, in opposite direction, capital M, the mass of the wedge, times its velocity. And the total momentum of the system of bodies remains the same. It was 0 in the beginning, and it must remain 0 in the process of motion. So at any moment of time, these two momenta should be equal to each other. So P sub x must be equal to mu, and from here we can find the relationship between the velocity of the wedge u and the mass and the velocity of the block m2. So if we substitute this expression here, we will find that m2 v cosine alpha minus m2 u equals capital mu. And from here we find velocity u as m2 v cosine alpha divided by the mass m plus m2. That's the relationship of the velocity of the wedge and the velocity of the block m2 at any moment of time. But this is just some discussion of what's happening. It's not the answer to the question of our problem. The question is, at what relationship between the two masses the wedge will remain at rest if the coefficient of friction is given here. So we have not started the solution of this problem. We have just discussed what's going on here, what's happening, how the velocities are directed. We have just started discussing this problem. We have not solved it. We have already considered in detail the motion of the body on the inclined surface, on the slope. In the absence of friction, and when there is some coefficient of friction, we have already solved this problem. So I will not repeat in detail the solution. I will just take the formula which we already know. We have just to indicate all forces acting on each body here. For example, this body is pulled down by a force of gravity m1g, and there is some force of string tension which I can denote by T, and the same force T is acting on the second block, and also other forces here, the force of gravity. Well, too many vectors and too many forces on the same picture, so let me draw it separately. A force of gravity acting on the second body, and the force of tension of the string, and the force of reaction of the surface, and the force of friction, which is F. And if the body moves in this direction, then the force of friction is directed opposite the velocity. If this body moves upward, then the force of friction will be directed again opposite the velocity. It will be, if the velocity looks upward, the friction will look downward. So, as we have considered this problem in detail, I can just write down the equations, the corresponding equations, without more discussion. the second Newton's law for this body, we assume that the bodies move here. Acceleration is directed to the right. So this body will move upward. And the second Newton's law for this body will be T minus m1g. And the second Newton's law for the second block will be m2, the same acceleration, equals what? m2g sine alpha minus t minus force of friction, which is coefficient of friction, m2g cosine alpha. I'm not discussing the details because we have already solved this problem. We have already derived these expressions. Now, if we add these two equations, then note that the force of tension in the string will cancel if we add these two equations. Then we obtain m1 plus m2 times acceleration equals m2 g sine alpha minus k cosine alpha minus m1 g. If acceleration is zero, then all this expression is zero. Only if the acceleration a is zero. That is, if the two blocks don't move. When this happens, this happens when we have some friction, some coefficient of friction. What we have written here refers to a situation when the block M2 moves to the right. But what will happen if this block moves to the left? If the body M1 is too massive and it pulls down the whole system and the blocks move to the left, what will happen in this case? The equation will be slightly different. What will change? Let's write down the new equations, which refer to the case when all the system moves in the opposite direction. What will be the difference? The difference will be in the force of friction. The force of friction will be directed in will have opposite direction. Now the force of friction is added to the force of tension in the string. If the body moves in opposite direction, then the force of friction will be subtracted from t. These two vectors will look in different directions. So, what we have already written here refers to the case when the two bodies move this body moves to the right. Now we will write the equations when this body moves to the left. What will happen? Again, m1a, acceleration of the first body. Now it will be equal to m1g minus t, and m2a, acceleration of the second body, will be equal to t minus k m2g cosine alpha minus m2g sine alpha. Such will be the direction of forces. T the force of tension in the string moves the body upward. It coincides in direction with acceleration. This is the force of friction, which pulls the body in opposite direction. That is why we have minus sign, and that is the projection of the gravity pull on the direction of the velocity. Again, adding these two equations, we add these two equations. Adding these two equations, we obtain what? The tension, the force of tension will cancel. And what we have is m1 plus m2 times acceleration. And here we will have m1 g minus m2 g sine alpha plus k g cosine alpha, plus because minus is here, minus times minus by minus gives plus. I have taken these two terms in a round bracket. That's why 2 minus give only 1 minus and plus. Simple algebra. And again, if the acceleration is 0, if the two blocks don't move, then all this is 0. We have two expressions. The first one written for the case when the block moves to the right, and the second one written for a different case when this block moves to the left. What does it mean that the two blocks move? Well, it means definite direction of all the forces, of all the vectors. And the direction is different in two cases. If the block moves to the right or if the block moves to the left, the forces are slightly different. The difference is with the force of friction. In the first case, it looks like the force of tension in the string, and in the second case, the force of friction will look in opposite direction. That is why two different equations. From each equation, we can obtain the desired relationship between the masses. We can divide this equation by m2, then m2 will vanish here, it will be cancelled here, and it will appear here. And we can divide this equation by m2, then m2 will vanish here, it will appear here. And we can find from this equation the quotient m1 over m2. It's easy to notice that the acceleration of free fall g will cancel, and what do we have in the end finally is m1 over m2, the quotient of two masses, equal to sine alpha plus k g cancelled k cosine alpha from this equation. And from this equation, m1 over m2, again, acceleration of free fall g will cancel, and what we have is sine alpha minus k cosine alpha. So the first equation refers to the case when the block m2 moves to the left. That's the velocity of the block m2. And this equation was derived from here, and this is the case when the block m2 moves to the right. Two different situations. So if if the bodies are such that they want to move to the right, then we have this connection between the masses and the coefficient of friction. And the subtle point is this. The two blocks want to move to the right, and they would move to the right if the coefficient of friction is slightly smaller. But if the coefficient of friction is large enough to stop the motion, then they will not move. The two bodies will not move. But if you reduce the coefficient of friction slightly, then the motion will start and they will move to the right. The same goes to the same consideration can be applied to this equation. The two blocks, the upper block can move to the left, but if the coefficient of friction is large enough, they will not move. If you reduce slightly the coefficient of friction, then the bodies will start motion to the left. So if the coefficient of friction is somewhere in between these two possibilities, then the bodies will not move. So if this relationship between the masses is realized, is valid for this problem, then the bodies will move to the left. If this relationship is valid, then they will move to the right. So if the masses are such that they are somewhere in between, less or equal to this formula, to this expression sine alpha plus k cosine alpha, or if the masses are slightly larger than this expression sine alpha minus k cosine alpha. If this is true, if this is what happens, then the bodies will not move. They will be stationary, and the wedge will not move, and all the system will be at rest. If the relationship between the two masses is such, the difference between the two masses is not very large and not very small, then all the system will remain at rest. Suppose the coefficient of friction is 0. Just assume that this is 0. Then we will see that the relationship between the masses will be what? It must be larger or equal to the sine alpha, and at the same time less or equal to the sine alpha. It means that if coefficient of friction is 0, then m1 over m2 must be equal to sine alpha. And on this condition only, the bodies will remain at rest and the system will remain at rest. That is, if no coefficient of friction, if no friction, then only at this particular relationship between the masses of two blocks, they will remain at rest. They will not move. They will balance each other. The two blocks will balance each other, and there will be no motion. But if the coefficient of friction is different from other than 0, then this will give you slightly smaller than sinus alpha, and this expression will give you slightly larger than sinus of alpha. And so the relationship between masses will have some interval, some possibilities for the masses to be within some interval, and so that the bodies don't move and remain at rest. If you violate this inequality, you must take either very large, very heavy block M1, and then the bodies will go to the left, or you must take very heavy block M2, and then the bodies will go to the right. You have to violate either one inequality or another inequality, and then the bodies will move. If you don't violate inequalities, if you obey this condition for masses, then the whole system will remain at rest. That's it. That's the solution of this problem. We started this problem by realizing that we have a complicated system of bodies, and if so, then we must use the theorem for the motion of the center of mass of the system of bodies. And this theorem says that if no external forces act on the system, then the acceleration of the center of mass is 0. We started from this. And then finally we used the second Newton's law applied for the first body and for the second body to find the acceleration. And we applied the condition that the acceleration is 0. So we obtained all these conditions and final solution of the problem. So the final answer is, if the two masses obey the last inequality, then the system remains at rest. If this inequality is violated, then the bodies start moving either to the right or to the left. That's it. Okay. Another problem that I wanted to discuss. Very small and very easy. Problem number 81. Problem number 81. A massive homogeneous cylinder that can revolve without friction around a horizontal axis is secured on a cart standing on a smooth level surface. So we have a massive homogeneous cylinder which can revolve around about this point, and it's placed on can revolve without friction. It's secured on a cart that can move without friction on horizontal surface, on horizontal table. So a bullet flying horizontally strikes the cylinder and then falls down on the cart. So it strikes the cylinder and falls down. Certainly when the bullet strikes the cylinder, it starts rotating because of this push, because of this strike. Does the final speed of the cart somehow depend on the point where the bullet struck the cylinder? So the bullet could have struck this point, the bullet could have been aimed here, or the bullet could have struck this point. So if the bullet goes along this way, then the cylinder will start rotating here. If the bullet goes along this way, the cylinder, and then drops down, the cylinder will rotate will have different direction of rotation. And if the bullet struck here, there will be no rotation at all. The bullet will just fall down on the cart. So does the final velocity of the cart depend somehow on the point where the bullet struck the cylinder? Does the final velocity of the cart, does it remain on where the bullet struck? We have just a few minutes to discuss. So what's your opinion? in which case 1, 2, or 3, the velocity of the cut will be larger. In which case the velocity of the cut will be larger. What's your opinion? Three? Well, regardless of the place where the bullet struck, it always falls down on the surface of this cut and remains here together with the cut. That's it. The only difference is the rotation of the cylinder. At first, in the first case, the cylinder rotates counterclockwise. In the third place, the cylinder will rotate clockwise, and in the second place, the cylinder will not rotate at all. So in which case, the final velocity is larger. To answer this question, we must discuss the momentum of the rotating cylinder. In order to find the momentum of the rotating cylinder, I will draw it again, and I will consider some small section in it. If it's rotating, then on some distance r from the center, we consider a small piece of mass, delta m, and the same symmetrical piece of mass here, the same delta m equal to this, on the same distance r, will have the same velocity, but in opposite direction. So the momentum of this material particle will be delta am times v, and it will be directed here, the momentum. And the momentum of this particle will have opposite direction, but equal in magnitude. So these two vectors added together give you 0. And so all other points inside this sector of the cylinder, all other points will give, in result, after we add these two momenta, will give 0 momentum. So rotating cylinder has 0 momentum. Regardless of the speed of rotation and regardless of the direction of rotation, the momentum is 0. It means that we don't have to take rotation into account in this problem. And whatever the place where the bullet struck, the final velocity will be the same, because there is no momentum of rotating cylinder. It may rotate counterclockwise if the bullet strikes here, or it may rotate clockwise if the bullet strikes here, and it may have 0 rotation, no rotation at all if the bullet strikes here. It doesn't matter, the final velocity will be the same. That's it. Simple considerations give you that the momentum of rotating cylinder is 0. It means that the velocity will be the same regardless of the place where the bullet strikes. That's it. Well, that's the end of our lecture. Thank you.